Hello everyone, welcome to my video. In this video, we are back to discuss relative motion, and this will conclude our journey in chapter 3. This section is more of a refinement of what we learned in section 2.8, as I'm bringing the same content as we saw before. The purpose of this section is especially to see if those concepts we learned, such as momentum, work, and energy, can be applied to relative motion scenarios. We will start with having a fixed system, x, y, z capital, and a moving reference system attached to B. In this way, B is moving with acceleration AB, and A is moving with respect to B with a relative acceleration. We call this A relative, or A REL, means relative. From a third-person perspective, if he or she wants to get the absolute acceleration of A, then we can use the equation A acceleration of A equals to acceleration of B plus the relative acceleration. Okay, this is the equation we know. Now, we're going to multiply both sides with the mass m, and ma will give us force. However, be careful here. If you just look at the sum of the force F acting on A, you might end up thinking sum of F equals to ma relative, which is wrong, because Newton's second law does not apply to accelerating frames or accelerating coordinate systems. We have to consider the accelerating frame, and therefore the sum of F actually equals to m multiply AB plus A relative, which is the relative acceleration of A with respect to B. This is our sum of F, not just MA relative. We can move MAB to the left-hand side and get within the XYZ system, the moving system, sum of F plus minus MAB equals to MA relative. For a moment, you might think this MAB is a force. Theoretically, yes, sure, F equals to MA, and this can totally be a force. But in reality, we do not see that. On the diagram on the right-hand side, there is only one force, sum of F. There's no any other force. Therefore, this is a fictitious force, does not actually exist, but a result from the moving XYZ frame. It is here because we need to find a way to satisfy the Newton's second law, but it does not exist in reality. If we explore further, this will lead us to the D'Albert's principle, which use fictitious force to make moving system, dynamics, look like a fixed system, statics. Sort of a simplification process. We're now going to dive into this concept here, as this course we only focus on translating reference system with a constant velocity. That means your AB is 0. We'll look at this on the next slide. But this serves as a reminder that Newton's second law has limitations, and you need to be careful. As I mentioned, to simplify our life, in this course, we're going to only deal with moving frames with a constant velocity, and this will bring us AB equals to 0. Therefore, mathematically, sum of F equals to MA reality. This is actually true because Newton's second law holds for systems with a constant velocity and non-rotating systems. So we're not breaking Newton's second law. For constant velocity non-rotating system, since Newton's second law can be used here, therefore these equations can be used for relative motion analysis, including work energy equations, impulse momentum equations, and moment angular momentum relations. All these equations we learned can still be applied here. Depending on how observations are made, such as within a fixed system or within a moving system, the values of work, kinetic energy, and momentum are different. This is essentially the difference between absolute motion and relative motion. They are completely different, so we need to be very careful when solving problems by understanding first which perspective are we looking from. Is it fixed frame or moving frame? Let's look at one example here to test out some of the concepts we just learned. I have a 2 kilograms block slides on a frictionless floor inside the train. The train moves to the right at a constant velocity of 10 meters per second relative to the ground. Inside the train, which is the moving frame, the block moves forward at 3 meters per second relative to the train. The first step is to identify the variables, understand which one are absolute, which one are relative. So we have the v train, which is relative to the ground, or we can say that is absolute, 10 meters per second, and v relative of the block, 3 meters per second, which is relative to the train, the moving frame on the train. So we can calculate the absolute velocity of A is v train plus v relative equals to 13 meters per second. This is the absolute velocity of the box, and this is the velocity observed by a person from standing outside the train on the ground. For kinetic energy, they are different when measuring from different frames. In the fixed frame on the ground, we'll use the absolute velocity of VA, which is 13 meters per second, and T is 169 joules. And in the moving frame, we'll use the 3 meters per second, the V relative, to calculate the kinetic energy is 9 joules. So now you can see the kinetic energy is different, measured using different reference systems. Same happens for momentum. In the fixed frame, the G is 26, and in the moving frame, the G relative is 6 kilograms per second. They are also different. Hope this example gives you an idea about the difference when looking from different frames for relative motion. Here I put a summary of what we just did in on the previous 4 slides, like comparing the velocity, kinetic energy, momentum, looking from fixed frame versus the moving frame. I don't really have recommended readings for this section. Sample problem 333 is good to know, but I won't require you to do anything like that. And this concludes our section 3.14 as well as chapter 3, which is the longest chapter. Good job for keeping up this far. Thank you for watching. I'll see you next time.